this lesson, we're going to look at a couple more operations that we can do with sets. This time, we're going to look at the relative and absolute complements. On this slide, let's determine all of the elements in A, but not in B. So if we were to list all of the elements in A, you'd have 1, 4, 3, 2, and 5. However, we're not really interested in the elements in B, so we could get rid of 3, 2, and 5. These are the elements that A and B share. So the elements that are in A, but not in B, are the numbers 1 and 4. On this slide, let's determine all of the elements that are in B, but not in A. So if we were to go ahead and list all of the elements in B, we'd have 7, 3, 2, and 5. And once again, A and B both share the elements 3, 2, and 5, so the only element that's in B but not in A is 7. This kind of operation is called the relative complement. To denote this kind of operation, we will use a slash, B/A, and read it as the relative complement of A in B. Now, if I see B/A like this, I typically find it easier to think all of the elements that are in B, but not in A. On our Venn diagram, B/A is the following shaded region. Take a look at the following Venn diagram. Try to determine all of the elements that are not in A. Did you get the numbers 10, 7, 9, 8, and 6? So here are the set of elements that are not in A. Next, let's try to determine all of the elements not in B. Did you get the numbers 1, 4, 10, 9, 8, and 6? So here is the set of elements that are not in B. This kind of operation is called the absolute complement of a set. And to denote this kind of operation, we're going to use a superscript. And it's going to look like this. If we end up using this operation, we require what's called a universal set, and we're going to call that capital U. And capital U has to contain A. That is, A has to be a subset of U. And some students find it easier to think of A to the C as all of the elements in U, but not in A. On our Venn diagram, we need to first notice that we have a universal set U and that A is contained inside of U. The absolute complement of A is going to be this shaded region here. Next, let's look at a few properties of the complement operations. First, what is A/A? Well, in this case, we're looking for all of the elements in A that are not in A. Since all of the elements in A are in A, this is a special case. A/A is going to be equal to the empty set. What about A/the empty set? This means all of the elements in A that are not in the empty set. But there aren't any elements in the empty set, so in this case we see that A/the empty set should be equal to all of the elements inside of A. This slide gives a short summary of the properties that we just discussed. Next, let's try to figure out what happens if we do an absolute complement twice to the same set. So first, let's find the absolute complement of A. And that should consist of the 3 triangles that are outside of our set A. Now next, the absolute complement of this set is going to be all of the elements inside of U that aren't these 3 triangles. So all of the elements in U that aren't the 3 triangles are going to be these 4 quadrilaterals. In other words, we see that if we take the absolute complement of A twice, we get back the original set A. Our last properties have to do with the universal set U as well as the empty set. So what do you think the absolute complement of the empty set is? Well, this should be all of the elements inside of U that aren't in the empty set, but the empty set doesn't have anything in it, so the absolute complement of the empty set is going to be all of the elements, or U. What do you think the absolute complement of the universal set is? Well, in this case, we're looking for the elements inside of U that aren't in U, and there are no elements, so we're going to get the empty set. This slide is a quick summary of the properties of absolute complements. Let's work through one final example. Here, the universal set is going to be the first 5 natural numbers. A is going to be the set containing 1, 3, 5, and B will be the set containing 1, 2, and 5. What would A union B be equal to? Well, this should be the set of all elements in A added to all elements of B, but we already have 1 and 5 listed already, so the only missing element we need here is 2. So 1, 3, 5, 2. And of course, the order doesn't matter. Now next up, we need to find the cardinality of the intersection of A and B. But let's figure out what that set looks like first. So what elements do A and B share? Well, they share the elements 1 and 5. And now that we know what this set looks like, we know that the cardinality, or the number of elements inside of this set, is 2. All right, next up we have a relative complement. So we're looking for all of the elements in B that are not a part of A. Since A and B both share 1 and 5, the only element in B that's not in A is 2. And finally, we'll look at the absolute complement of B in our universal set U. B contains the elements 1, 2, 5, and the other elements in U that are not in B are 3 and 4. All right, my little epsilons, stay positive.